Okay, welcome back. This is 14.7, and what we're doing is cylindrical and spherical substitutions. And it's not a bad idea to think of these as kind of like trig subs. Right? So what you want to do is basically to simplify an integral into something that's easier to integrate. Um, Usually in Calc 1, though, you don't have that kind of geometric intuition that goes along with it. It's just kind of, I'm going to do a substitution so things cancel out and all that jazz. Here, though, there's always this geometric kind of intuition where we could visually see that, okay, this integrating in this new coordinate system would be a lot easier than the old coordinate system because the coordinate system is better suited for creating these types of curves, right? So the first system we look at is cylindrical, which is basically just the polar coordinates plus z. And so you may remember on the first test I gave you a formula sheet where I basically, this is your x, this is your y, and this is your z axes. And then we could describe a point x, y, z, but we can also describe it sort of with a cylindrical coordinate, which is the polar coordinate plus z, right? So this point here in space would be r comma theta comma z. Okay. The coordinate conversion formulas for x and y are just what we think they are for the polar coordinate system. So r, where in this case r is this distance right here. Sorry, it looks like a p. Okay. This is r. And then cosine theta. And then y is r sine theta. And then z will be z. Okay. When you do your substitutions, it's kind of a straight substitution. It's pretty easy. You just have to always add in that factor of r. And it's kind of like when you do u substitutions, you generally have to add in a factor to even it out, so to speak, right? So in this case, the triple integral, if you've given a triple integral in terms of x, y, z, and you want to move to polar or spherical, cylindrical coordinates, you substitute in r cosine theta for x, r sine theta for y, and then you could just leave z alone. This should be a z. Okay? And then dv, instead of dv will equal dz r dz. So there's always that factor of r in there. R dz dr d theta is kind of how you want to integrate it. Okay, we won't worry about change in order of integrations for the cylindrical coordinates. Okay. At the end of the day, what is really happening? Well, you're adding up a bunch of little, not cubes, but cylindrical cubes, and the geometry of the cylindrical cubes is a little bit different, and it causes you to have to change this factor. Okay, so it seems like this cube over here is basically like this cube, but deformed in such a way that we will have to replace the volume increment with this new formula. Okay. Okay, you could go through and look in the book and figure that out, figure it out, see what the cube looks like and stuff. I have it in my notes online too. But anyways, let's just try to do this one. I think it's easiest just to think of it as a substitution, a u sub. Okay. So you have a triple integral of r dz dr d theta. And I'm going from 0 to e to the negative r squared, and then 0 to 3, and then 0 to pi over 2. They actually want you to sketch this thing, which is not the easiest thing to do by any means for a young calc student. but we'll try, right? So at least in this portion, this is just kind of the polar curve type deal. So in the XY plane, we kind of know what that is, right? So I'm going from r equals 0 to r equals 3. So that's just going to be a circle with radius 3. And then the running man is rotating from 0 to pi over 2. So in particular, it's this region here that I'm integrating over. Right? So for the surface part, the way I kind of thought of it was to first draw it in the RZ plane. Okay, so R is just R, and then Z will be on this axis. Okay, so your Z equaling 0 would just be the R axis, and then Z equaling e to the negative R squared would be, well, this might not be obvious to you, but it's a bell-shaped curve. Okay, the teachers use bell-shaped curves a lot, right? If you study statistics, that kind of thing will come up. Okay, so this is our bell-shaped curve for this thing. Okay, so for any R value, so for any distance value in this region, where theta is kind of stuck, so maybe let's say theta is equal to pi over 4 right here. You can imagine the cross section is going to be this object over top. Okay, so this thing would be kind of right here coming out at you. Okay, so what does that look like in this region? It's kind of like when they have these holiday decorations that you can kind of unfold. I should go buy one of those if I wasn't quarantined. I guess I could buy one on Amazon, but just for this one little example, I don't know if it's worth it, but you kind of unfold it and it opens up into a ball. So you get it as a piece of paper, and it has a bunch of paper inside of it, and you open it up and it's like a ball. Well, and on the inside, you're going to have a bunch of these, okay, as you open this thing up, and it'll kind of look like this. Ah, crud. I don't know. Right, and that 1/4 of a quadrant, you get something that looks like that for this one octant here. Okay, where each one of these curves is basically this curve right here. Okay, they want you to evaluate the critter, so we can do that. That's the easy part, I think. So with respect to z, that will just be r times z evaluated from 0 to e to the negative r squared, dr d theta. And then this will equal the double integral. I'm plugging in e to the negative r squared for z. So I'll have r e to the negative r squared minus 0, which will just be r e to the negative r squared, dr d theta. Okay. Then I need to pull off a substitution for that. So u equals negative r squared. du is negative 2r dr. And then dr is negative du over 2r. So there's my sub. So this integral will become the double integral of r e to the u times negative du over 2r d theta. Okay. Then I can pull out the negative 1 over r, the negative 1 over 2, and then the r's will cancel. So I'll have negative 1/2 integral of the integral of e to the u du. The integral of e to the u is just e to the u, so let's write e to the u. And in our case, u is negative r squared, so let's cut to the chase, put negative r squared there. And then I have to evaluate that from 0 to 3, and then d theta. Okay. And then I'm going to go ahead and evaluate that. So negative 1/2 times the integral of e to the negative 9 minus e to the 0, which is 1, d theta. And then integrate that with respect to theta, so negative 1/2 times e to the negative 9 minus 1 times theta, evaluated from 0 to pi over 2. And then you could just plug in your pi over 2 and look in the back of the book, see if it's right. Okay. And I'm pretty sure it is. So this is negative pi over 4 times e to the negative 9th minus 1. Okay, let me look at my notes, make sure that's right. I wrote it in a funny way, but that's right. Okay, so that's cylindrical substitutions. Now we want to do spherical substitutions. So cylindrical substitutions are good when you're dealing with, I don't know, cylindricals are good for when you're cylinders, basically. Yeah, so when you're integrating over a circular region or you're dealing with some form of cylinder, it's good. Spherical coordinates are good for spheres, sphere-type objects. So section 2, I guess that makes sense, right? Spherical, sphere. So anyways, a spherical coordinate system, if you recall how to create these things, basically, you'll have some point here, which is kind of dictated by this angle phi and this other distance rho, which is this length, which is kind of like an r length. And also this angle down here, which is the same angle from our cylindrical coordinate system, theta. Okay, so you can describe the point as rho, comma, theta, comma, phi. And then this here is a right triangle. So you can kind of use all kinds of stuff from your cylindrical coordinate system to figure out the conversion formulas, if you want to go through that again. But long story short, x will be rho sine phi cosine theta. Y will be rho sine phi sine theta. And then z will be rho cosine phi. Okay. So the substitution here, a little more complicated. And in order to adjust the integral with your kind of u substitution, or in this case, spherical substitution, the factor before in the cylindrical was r, right? So we had to replace it with z, r, dr, d theta. Here, it's more complicated. So before, for cylindrical, you would have to replace your delta v with r dz, or delta z, delta r, delta theta. Now with spherical, it's even more annoying. It's delta v is replaced by rho squared sine phi, delta phi, delta rho, delta phi. I hope I'm saying phi instead of rho. Delta theta. Okay, so in the next section, in what is it? The Jacobian section, kind of tells you how to figure out these substitutions. Okay. Well, the weird thing, if you read the Jacobian section, is it kind of seems like it's all going in reverse. It's like, if I'm doing this forward substitution, why are they giving me this formula that's going in reverse? It's a little confusing, and I honestly don't even know why they do it that way. It probably has something to do with the history of math, or it's something that's more advanced, and I'm just not seeing it because I don't study Calc 3 for fun. But I mean, I like right now I study more set theory. So set theory is really important for foundations and later math, which is, you know, if you keep studying math, hopefully before you start taking hardcore like real analysis and things like that, you have a class in set theory and a class in proofs to help you along. But yeah, I'm more into set theory right now, so I apologize if I'm sort of speaking out of ignorance. But anyways, I think this is a good intuitive way to think of it. It's a substitution. Just like when you do U subs in calculus, you always have to replace your du, right? So if you did like a sub for, I don't know, x minus 5 cubed dx, your u would be x minus 5, and then du, this isn't a very good one, let's put x squared, right? It would be 2x dx. So dx would be du all over 2x. And this thing would kind of be like the thing we're doing, sorry. If you did a u sub for this integral, you would u is x squared minus 5, and then you're finding dx. Okay, so you're replacing dx with du over 2x, and you hope you have some simplifications and stuff. For here, you're doing the same thing, right? But instead of having just a plain old dx, you have dx, dy, dz, and you're doing your substitution. So you end up with this monsterish kind of nightmare going on when you do your substitution, which corresponds kind of to this 2x thing that's floating around in here. Okay, so anyways, let's take a look at doing one of these things. This is number 33. Find the volume inside the sphere and outside this this cone. So when you're working with something like a sphere, it's helpful to go to cylindrical coordinates. So the geometry almost tells you the kind of U sub that you need to pull off. So find the volume inside x squared plus y squared plus z squared equals 9, and outside z equals x squared plus y squared square root of, that's the cone, and then above the xy plane. Okay, so you're probably not as familiar with working with a cylindrical idea, but I'll try to walk you through it. Okay, so the picture of this thing, you have the above the xy plane means just the top hemisphere of the sphere with radius 9, or radius 3, excuse me. So I have the top of a sphere, and then on the inside of the sphere, I have a cone. Okay, so the cone will probably be peeking out maybe right here. Okay, and that's on the inside. This is all in the XYZ space. So this is 1, 2, 3, 1, 2, 3. Okay. I kind of need to know the region I'm integrating over, so I will need to know the projection of this intersection with the sphere. So I need the intersection of the sphere with the cone. And to do that, before, in one dimension, we just set the equations equal to each other. We do a kind of a corresponding thing here. I'm going to plug this into here and see what happens. So I'll have x squared plus y squared plus z squared, which is x squared plus y squared, equals 9. And then what do you get? Well, you get a 2x squared plus 2y squared equals 9. And then that's just a circle with radius square root 9 over 2. So x squared plus y squared is equal to 9/2. So it's a circle with radius square root of 9/2. Okay. So the region I'm kind of integrating over is somewhere in here. I don't know if that's even going to be necessary to know that region, but there it is. Okay, so here we go. I have this triple integral. I'm trying to find the volume of this region. And what I want to do is, so I'm thinking of the stuff inside the sphere and outside the cone. Okay, so it's kind of almost a donut region, but not really, right? Okay, so I'm going to set up my integral. All I need is volume, so I don't have this other fourth dimensional factor to worry about. So I'm just integrating 1, basically. And then I have my dv, but I'm going to do a substitution, right? So I need rho squared sine phi and all that jazz. So rho squared sine phi, and then we'll do the order d phi, d rho, d phi, d theta. Okay. Okay. So in the YZ plane, we can kind of look at this object that we're worried about. And this angle here is the phi angle. Sorry. So if I looked at this head on and the YZ plane, I would kind of have this, and just that would be in this region here. Right? The phi values seem kind of obvious for what we need. We need, right, this region here to find the volume of. So phi must be going, and remember phi works like this. It goes from 0 to pi over 2. Okay, so in this region I'm going from 0 to probably like pi over 4 or something. I need to find where the side of the cone intersects with this circle. Okay, so what is this line? Well, in the YZ plane, if I let x equal 0, I'll get z equals the square root of y squared. So z would equal absolute value of y. In particular, this curve. So I mean, you're getting 2 curves out of it. You're getting that curve and this curve from the plus minus y. But we just care about this curve here, which is y. So z equals y. And then this curve here is from the sphere itself. So if you let x equal 0 in this equation, you get y squared plus z squared is 9. Right? And then to find the intersection point, I could just replace z or y with its other. I'll replace z with y squared, or sorry, z with y. I get y squared plus y squared is 9. And then 2y squared is equal to 9. So y squared is equal to 9 halves. So y is going to be square root of 9 halves. Right? And then y is equal to z, so z will also be square root of 9 halves. Okay. So this point right here, if you think about that as a right triangle, that point with square root 9 halves, comma square root 9 halves, tells you the sides of this right triangle. And then the tan of this angle in here, we'll call it alpha. It must be equal to this over this, square root 9 halves over square root 9 halves, which is the same as 1, right? So alpha must be pi over 4. Okay, if alpha is pi over 4, then phi is also pi over 4. So at least the phi integral part is going from 0 to pi over 4. The theta part, because we're just dealing with this, well, are we dealing with the whole thing? Yeah, we're dealing with the whole region and the underneath the hemisphere. Theta is being traced out from 0 to 2 pi. Okay. Those are the easy ones. Now I need to get rho. Okay, so rho is this length right here. Okay. And so I want to go from rho equals 0 to rho equals whatever this distance is to this point right here. And did I screw that up? Yeah, because I went from here to here on phi. Sorry, you need to go from here to here. So this would be, sorry, pi over 4 to pi over 2. It's this region I'm after. So if it was this region, this upper triangle region, I would have to go from pi over 2 to, sorry, from 0 to pi over 4, but it's not. I need to go this region, so it's pi over 4 to pi over 2. Okay, so it's always coming from the top down, which is the weird part. Okay. Anyways, then on the arm, the row arm, what is this? So this picture here is the intersect of the cone with the sphere. So this here is the sphere, and I need the radius to always be the same. It seems like the radius is screwed up, right? But the radius of the sphere is kind of what I'm after. So this picture is, the picture's fine, sorry. It's this length I need, this row length, right? So what is that row length? Well, because this is the sphere, it has to just be 1, 2, 3. Okay, so the length is always just going to be 3 for any position, any phi position, and in that range. Okay. Okay, so my row needs to go from 0 to 3. That was incredibly painful for me. Okay. Then all you have to do is integrate the guy. So hopefully you made it with me. Sorry, it's not every day I do spherical coordinate substitutions. Okay, so I need to then, what do I need to do? I need to integrate the thing. So first with respect to row, so I have on the inside rho cubed over 3 evaluated from 0 to 3 of sine phi d phi d theta. Okay, so just going from here to here, integrate the row part first. Rho squared is rho 3 over 3. I still have a sine phi to deal with, and then d phi d theta. Okay. Okay, so this will be the integral of 3 cubed is 27 over 3 is 9, and then minus 0 over 3 is 0, so I can factor out the 9, and then I have sine phi d phi d theta, and then the integral of sine is negative cosine, so I'll factor out negative. I have 9 integral of cosine of phi from pi over 4 to pi over 2. And then d theta. And then I'll have negative 9. So the integral of cosine of phi will be, whoops, I got to evaluate first. So cosine of pi over 2 is going to be 0, and then minus cosine of pi over 4 is radical 2 over 2. And then d theta. Okay, so this will be negative 9 times the integral of negative root 2 over 2, so this will be plus 9 root 2 over 2, and then 1 d theta, which should be 9 over 2 root 2 times theta, and then times 2 pi, and hopefully that's the answer. Let me look at my notes. Yay! So it's equal to 9 over 2 root 2 times 2 pi, which is equal to 9 root 2 pi. Okay, well, you know, on a test, I probably wouldn't put one of those on there, but if for some reason, God, I don't know where you would be forced to have to do this, but if for some reason you did, hopefully you could kind of look back in your notes and finagle an answer if you need to. Okay, so that'll do it, and we'll see you in the next video, Jacobians. And like I said, Jacobians, you can kind of just look at it as U substitutions, okay? The book will try to make a huge deal out of it, and when I do that section, I'll try to go along with the book and at the same time kind of think of this as a U substitution. But like I said, when you look in the book, it's going to, if you really get into it, it kind of seems like they're doing it in the wrong direction. They're doing the U sub and the substitution for, like in our case, dv, substituting it with rho squared sine phi d phi. So we're doing a substitution for dx dy dz with all of this stuff. Seems like they're kind of doing it in reverse. And what you would have to do in that case is kind of divide out by this factor. Um, so it's a little weird, but get in there and try to read it. And it's good practice to have to read technical information, because I assume all of you will go on to be engineers and stuff, and you have to read technical stuff all the time. So it's good practice. Anyways, I'll see you next time.